Is it one of the losing stuff? But also comes there's no. There's one of he's probably gonna sound like that. But when you pull your hair back, now all this is sound.
What's today? Okay, guys, this is off of your original packet. There were some things that I forgot to include in your original packet. So there's that second additional packet for these couple of sections. So I'll kind of jump back and forth between them. But I think today we're just going to focus on getting through power rule. Okay. Now, power rule for derivatives was the most common derivative rule that you used. And likewise, we have also a power rule for antiderivatives. And this will be the most common rule they use on the antiderivative side. It's going to feel a lot like derivative rules for power rule for derivatives, but we're just doing the inverse procedure. So let's just review power rule for derivatives. If I had the function x squared, my derivative would just be what? 2x, right? And the process that we go through is we bring the exponent down in front of the variable and then we multiply. And then what do you do with the original exponent?
Subtract one.
Good. So let's say you wanted to go back to where you came from. Then instead of subtracting the exponent by 1, what are you going to do? Add. We're going to undo our derivative. And then instead of multiply, we're going to divide. So that is basically our power rule for antiderivatives. We're really just going backwards from derivative power rule. So imagine if I want to get from 2x back up to x squared, I'm going to have to increase my degree by 1. And I have to divide by 2 because of this number here. And this ends up being giving me x squared. Now, our notation for derivative is d over dx. But if I want to find the antiderivative of an expression, then this is the notation I'm going to use. This is an integral notation. It looks like an F-shaped notation there. So the integral of u to the n du, and u we use u because we want to represent. It's like chain rule where we want to represent a larger expression, but it also works for x. Let me do the x version first. So the integral of x to the n dx is equal to, and then x to the n plus 1 over n plus 1 plus c. So the power rule process is this piece right here. Now the integral and dx, those are just notations. We're not doing any mathematical computations with those notations. It's just like d over dx. So d over dx is just notation. We knew that it just meant find the derivative. If you see this integral notation and dx, that just indicates that I want to find the antiderivative of some expression. Now the d over dx kind of has that reminder of slope, right? dy over dx, change in y over change in x. There's that slope relationship here. Here, we're going to see that area relationship. That dx is that width component of your rectangle. X to the n is the height component of your rectangle. So we see that area component show up just like how we see a slope component show up with the derivative. This plus c is the constant of integration. I'll talk in a bit why we need that plus c. So this is the rule that we're going to apply, but down the road, for more complicated expressions, we're going to use the letter u to be able to expand to more complicated versions. It's kind of like chain rule for antiderivatives, basically. So a couple of notations here. So we talked about how there's that integral notation. The expression that you're working with is called the integrand. Dx is your, this identifies the independent variable. Usually it's dx, because usually we're dealing in terms of x, but it could be dy, it could be du. Okay. It just identifies what variable you're working with. And then we have the antiderivative, and then plus c. And plus c is your constant of integration. So let's consider the following functions here. I have x squared plus 5. I have x squared minus 13. I have x squared plus 126. So if I were to ask you, what is the derivative of all these functions here? 2x. So we have all these functions that share the same derivative. Or let me ask you this. How many functions share the same derivative then? Infinite, right? As long as I have a constant, it's going to be something in that family of x squared. Anything in that family of x squared is going to share a derivative or slope behavior of 2x. So since we can add a constant to any of these functions and still result with the same derivative, the antiderivative of a function will be in the form of f of x plus c. Right? Because we have more than one function that share the same derivative. So if I want to find the antiderivative of 2x, it's x squared plus this family of functions plus c. Okay. And the visual representation of this is if I had a graph that was this versus here, they all will share the same slope behavior, right? Every point here is going to be a slope of, let's say, -5. Every point here will be 0. Every x value here will be 1 or 3, right? And they all share the same slope behavior, even though they have different y-intercepts, right? So the process of integration is called anti-differentiation, or taking the indefinite integral. So the indefinite integral is going to result in a function. But we're also going to be able to in a next day or two, we're going to find the definite integral. We're going to be able to take that formula and actually arrive at some area related number that's going to tell us the area under a curve. But right now, we're just focused on creating that area finding formula, that function. It's just like how when we found the derivative, we just focused on finding the derivative first, slope finding formula, and then down the road, then we plugged in a value, and then we actually are able to find a number that's associated with that slope. But we're going to focus on just building that expression first. So do you remember how with derivative power rule, we had all these conditions in place? We had to rewrite our expression as a rational exponent. We had to bring our variables in the numerator, and we have to make sure we expand our terms, no parentheses. So the conditions that we have for power rule for derivatives are the same conditions that we require for power rule for antiderivative. Okay, let's go to the next page. So let's look at integral of 7x dx. Now, as soon as you find your antiderivative, your notations drop out. Your integral notation drops out. Your dx goes away. It's just whatever your antiderivative is and then plus c. So again, the way that we take our power rule is we add 1 to the exponent, and then we divide by the new exponent that we just found. So 7x becomes what? 7. X becomes x squared over 2. Yeah, and then plus c. So we add 1 to that exponent, and then whatever new exponent you see, you're going to divide that down. just convinced that this works. If I were to find the derivative of this, I should take me down to 7x, right? So the derivative of 7 halves x squared is just bring down the 2. 2's cancels out. 7x to the first power. So 7x is basically the derivative of 7 half x squared. Imagine all these problems are at the derivative level, and we're trying to make our way back up to the function level. Okay. Number 2, 7x cubed becomes. Yep. Now, 1, 2, and 3, we didn't do any cleanup, right? No radicals in the way. All our variables are in the numerator. No parentheses to that's throwing our power rule off. So number 3, we can just apply power rule how many times? 3 times. Okay, try that. Plus what? C. Now, you may be thinking, well, aren't there 3 C's here? Because each one will produce their own C, so you could say that, plus 3C. But 3 times the constant is still a what? It's still a constant. So it just gets absorbed into just one big constant. So x squared plus x cubed minus x to the 5th plus C. Yes.
So the plus 3C, I mean, that not make much sense because the whole reason we add a plus C is because we're assuming that there's going to be some constant that we're introducing in the.
Exactly. Yeah. So there's still, yeah, there's no need to put that 3C. I just wanted to show this because some students were asking, wait, shouldn't it be plus 3C and why isn't it 3C? You could reason it that way, but then you can also make that 3 disappear into that C. Number 4, we also want to do a power rule for antiderivatives, but what's getting in the way here? Parentheses. That's expanded out, yeah. So we can't just distribute, we got to FOIL it out. So try that. So we got to FOIL out, get rid of all the parentheses, just like how if you were finding the derivative for this expression, the same cleanup efforts is required. There is no chain rule. We have something called use substitution, which we're going to learn later, which is kind of like the inverse chain rule. It's like chain rule kind of pulls everything apart, and use substitution is going to put everything back. Okay, every term gets power rule treatment. 9x cubed over 3 minus 6x squared over 2. Now, what is that? What do you think the 1 is going to turn into?
X.
Good. 1 is going to turn to x. You know how with derivatives, every degree 1 will turn into a constant. But now we're going the other direction. Every constant is going to rise up to a degree 1. So every term is going to increase this degree by 1. I see some students, though, they see that 1 and they get derivative process in their head and they make it go to 0. We don't want to do that, right? We want to make sure we're going the other direction here. So plus x, and then don't forget plus c. You can always double check your work. You should be able, if you find the derivative of this, you should be able to make your way back to your starting process. All right, number 5. what do we need to do before we apply power rule? Yeah. So the process that I did with power rule for first semester for when we did derivatives was split up into individual fractions. Okay, and we're going to apply that same process here. Here is an issue that students experience is that with derivatives, you had a second option. You could have went through quotient rule. Okay, there is no quotient rule for antiderivatives. We have something called U substitution, which can handle certain fractional values. But if you start applying quotient rule, f prime g minus f g prime over g squared, that's that doesn't exist for antiderivatives. But let's do the same cleanup efforts here. So I'm going to split up into individual fractions. And if I do that, I can basically split this up into two individual problems. And if I can get them to be independent of each other, then I can do power rule once I have them cleaned up. I can subtract exponents to get my denominator to come up. And now power rule. I'm adding 1 to the exponent. 1/2 plus 1 is 3/2. Whatever exponent I find, I'm going to copy that number below my in my denominator. And usually what I like to do is if I see a fractional value in the denominator, I just like to flip up at the reciprocal to make it a little bit easier to interpret. Number 6, I'll have a different independent variable, but it's the same process. That dy indicates that my independent variable is now y. But see if you can get all that cleaned up, get the y's to merge into one variable, and it needs to be where before we do power rule? Numerator, okay, try that. So the y's combined, I add exponents. 1 plus 1/2 is 3/2. I need to move it up, so y to the negative 3/2. And I apply power rule for that y to the negative 1/2. Sorry, y to the negative 3/2. Add 1, that becomes y to the negative 1/2 divided by negative 1/2. Dividing by negative 1/2 is the same thing as multiplying by -2. So -6, and I want to resolve my answer, so bring my resulting variable back down to the denominator so I can get a positive exponent to show, and then plus c. Any questions with 6? Okay, keep reminding yourself that when you do your antiderivative, we don't want to include that integral and dy notations anymore. Those completely drop out. You're just left with your expression plus c. Yes.
On questions like that, you don't want to, like make y into a radical, right?
You can.
You can, but
Yeah, I'm just always gonna leave it as rational exponent, but if you went to radical, no issues there. It's up to you. Okay, number 7 is just a more complicated version of number 5. So, what's our process there with number 7? Yeah. Mm-hmm.
By the, final.
Yeah. Yeah, so expand, radical, resolved. And my preference is split up into individual fractions. If you bring that x to the negative 1/3 up, you can. What I see a lot of students do is they bring that x to the negative 1/3 up, but they forget to distribute through the rest of the numerator. And so that just messes things up for some students. But I'm just going to split up into individual fractions like how I did with number 5. So I'm forcing every term to deal with that denominator. And now I'm also basically able to split up into 3 smaller problems. And then once I have them all individualized, clean them each up, and then apply a power rule for each of them. Yes.
Number 5.
Yeah, so this was x over x to the 1/2. And if I have basis, if I'm trying to divide x, I'm going to subtract exponents. So 1 minus 1/2 is 1/2. So here are my cleanup efforts, one step at a time. Distribute that 3x to the 1/2 through. So I got to do common denominators here. 1/2 minus 1/3 is same thing as 3/6 minus 2/6. 3/2 minus 1/3 is same thing as 9/6 minus 2/6, which is 7/6. 5/2 minus 1/3 is same thing as 15/6 minus 2/6, which is 13/6. Okay, we haven't done any calculus yet. We've just gotten our problem up to the starting line. So now we can apply a power rule for each term. Dividing by 7/6, the same thing as multiplying by 6/7. Okay, any questions with power rule? Number 7, that's as hard as power rule is going to get, just like with derivatives. A lot of students want to try to do quotient rule or, yeah, so just, we had that practice first when we did power rule for derivatives, and hopefully this feels just like a similar setup. Because the way we clean up is the exact same way. We're just doing a inverse procedure to get to with our calculus step.
That's on your last step, that still has the integral sign on the last, 3x to next to dx, does that say 13 over x to the x prime?
This part right here?
Yeah. Or 13 over 6, I mean,
Yeah, 13 over 6, that's for this piece here.
okay, yes.
So,
Make sure that reads 13 over.
yeah, 13 over 6, yeah. This is before my power rule, yeah. Okay. Okay, page 22. Let's recall our derivative trig rules. I like to organize it in this form, 2 columns. My C functions are alphabetical order, COS, COT, CSC. Sine, tangent, secant are the first column. The ones next to each other, across from each other, have similar, the forms look similar in the way that the derivatives look. So what's the derivative of sine of u? Cosine of u times u prime. Okay. So that's just to remind us, that's just chain rule, right? But if it's x, then that u prime will be just 1. Okay. Cosine's derivative? Negative sine of u times u prime. What's tangent's derivative?
It's square u.
Yep. Cotangent's derivative. Yeah, similar form, right? Negative cosecant squared u times u prime. We talked about how tangent and secant, their derivatives involve each other. And then cotangent and cosecant copies it as well. They involve each other. Okay, secant's derivative. Secant u, tangent u times u prime. Okay, cosecant's derivative. Negative cosecant u, cotangent u times u prime. Okay. All right, are you good? You guys feel comfortable with these rules? Okay. So I want to convince you that if you know these rules, there's no need to memorize the integral trig rules. Now, having said that, we do have some additional ones that are log related that will come back to. But the original 6 integral trig rules, we should not have to memorize them. I don't have them memorized. We simply are working backwards from them. Okay. So let's just imagine we're going backwards here. What do you think the integral of cosine of u will turn into? Sine of u plus c, right? We're just undoing it. Okay, so find that rule and write it down. Cosine of u is simply sine of u plus c. Okay. What do you think the antiderivative of secant squared of u du would be? Tangent of u plus c, right? Okay, find that. Sorry about the stray marks there. I think some of them looks like they have minus negative signs there. So there's just printer I had a bad copy to give you. So okay. What do you think secant tangent u's antiderivative would be? Secant u plus c. Yeah. Okay, these we got to be careful here. What do you think sine of u's antiderivative would be? Yeah, so if I take the integral of negative sine, it would be cosine, but if I take the integral of positive sine, the negative has to be resolved somewhere, so it's going to get dragged to the other side. So the antiderivative of sine will be a negative cosine u plus c. what do you think the integral of cosecant squared u would be?
Negative.
Negative, yeah. The negative has to go somewhere, right? Negative cotangent. What's cosecant u? Cotangent u is antiderivative. Negative cosecant u plus c. So this is what I suggest on the AP exam. I always tell students, when you get your non-calculator portion, go ahead and write these 6 rules in front of you, because you're not really looking at 6. This is actually how many rules? 12, right? Because you really can use this to help you get to the other 6 rules. If you know these rules, there's no reason for you to memorize them, or to hopefully to not have any trouble with them. Okay, so we okay with that process? Yes.
We also like divide each trig function by like u prime.
Okay, so yeah, let me talk about that. That u prime is really in place of this du. So the cosine of u, think of that u prime as du. So cosine of u du is sine of u plus c. Now that u prime is taken care of within the u, so don't have to worry about that portion there. Okay. So it really is as easy as reading it from your original derivative rules. But having said that, these two give students trouble. You know why?
It's like those signs are.
Yeah, because we're used to seeing sine's derivative as positive cosine, cosine's derivative as negative sine. So when we see that, it takes a minute for us to kind of process that, right? It's like, wait, why is cosine a positive sine, and why is sine all of a sudden a negative cosine? Because we're working backwards from the derivative rules. So these tend to give students a little bit more trouble because of our derivative process that we've learned to begin with. Okay, so just be aware of that. And also, the C rules, the C connected with negative still applies for cosecant squared and cosecant, but it doesn't quite apply anymore with cosine for antiderivatives, because the integral of cosine is positive sine. So that's another issue that students have. They're like, well, all this is negative, so shouldn't cosine also be negative? But we're going the other direction, so these tend to give students some trouble. All right, let me see if I can start into page 23. I don't know how much I can get into it, but we can also talk about particle motion from the antiderivative perspective. So displacement and distance, we've talked about displacement distance from position standpoint. Now let's talk about position and displacement from a antiderivative standpoint. So displacement is how far you are from where you started. So displacement is just the integral from a to b of v of t. So basically, right now, you just have to understand that if I look at the area under my velocity function, so whenever we see an integral is basically just going to give us information about the area under that graph. So if I accumulate velocity, we know velocity is the derivative of position. So if I take the antiderivative of velocity, it'll give me something that's position related. So that's displacement. So if I accumulate all my velocity over a period of time, that's going to give me how much distance I've covered, which is displacement. And distance is the total amount that the particle has traveled. So sometimes you may have graphs that are sitting above and below the x-axis. And if that's the case, then you're moving forwards and backwards. And anything above the x-axis indicates how far the particle has moved in the positive direction. The area under the x-axis will indicate how far the particle has traveled in the opposite direction. And if I want to find the total distance, I can just treat everything as a positive area. And if I find positive area, then I know that even though he's moved left 3 units, we can still count that as a positive 3 towards distance. All right, so example here. Suppose the graph represents the object's velocity function. The number inside represents the area of that region. And we know the area is going to represent displacement, how much he's traveled in what direction. So here, A to B, this is your time interval here. So what does that 10 tell us? Yeah, 10 units to the right. And then it's going to do what?
Travel 2,
Stop, turn around, and travel
2 to the left.
2 to the left, stops, and then travels 3 to the right. Yeah, so displacement, integral from A to B of V of t, is simply keeping track of your positive and negative signs. Right? Where is this object going to end up after it moves left and right with these numbers? Sorry, -2. Not for displacement. Yeah, for distance we will. So this object is going to end up 11 units to the right of where he started. But the distance is counting his steps. Make sure your absolute value just goes around your velocity and not around your integral or your dt. So now, what are we going to do with all these numbers? Make them all what?
Positive.
Positive. So even though he ended up just 11 units to the right of where he started, in total, he's going to take 15 steps. He's going to travel 15 units. Okay, final thing, and then we can stop. This is just going backwards with position, velocity, acceleration. We know that position's derivative is velocity. We know velocity's derivative is acceleration. So if we go backwards, that's the antiderivative relationship. The antiderivative of acceleration is v of t plus c. The antiderivative of velocity is s of t plus c. Just undoing our derivative process when it comes to antiderivatives. All the relationships is still the same in terms of increasing, decreasing speed. Same signs would indicate increasing speed. Opposite signs would indicate decreasing speed. Okay, guys, no homework tonight. Some of these problems we haven't learned how to do them yet, so we're going to push things back a day. So no homework tonight. We'll pick up tomorrow. Okay, I have your quiz mostly graded. Grades are due Thursday, so I need to get them in. I should be able to get them in later today. And I'll hand them back later this week. All right, come get your phones.
And I still.
Yeah, we did.
Like, we took meetings, like, over.
Uh-huh.
It's like.
Figuring